All right.
Say, welcome back to the
So, momentum conservation. Let's talk about what I want to show you is how like momentum conservation can be represented mathematically, because ultimately we're going to need to understand how momentums add up before and after a collision. I'm going to talk about the explosion as my example. So I'm going to draw a large object and label B for blue, and then I'm going to put the smaller one next to it and label it R for red. Those are the two carts. I'm just going to keep it that simple. Okay, and we're going to use the picture to kind of build up our understanding. So, when the carts push apart, when that spring does its job and pushes them, what happens is that each cart pushes on the other one. Okay? So, for example, the blue cart pushes the red to the right. We're going to call that force on red. So F with an R, and I'll represent it with an arrow. So this is the force acting on R. It's FR, force on red. By Newton's third law, the law of action and reaction, we also know that red pushes back on blue, and that pushes back with a force that we'll call FB. And yeah, those forces are equal and opposite, so you can put tick marks there because that's how Newton's third law works. They are interacting through the spring. Now, what I'm going to do next is I'm going to write down this. I'm going to write down Newton's third law for those forces by saying that negative FB is equal to FR. In other words, the forces have the same size, but they have the opposite direction, and that's where that negative sign comes from. I got one force to the left, I got one force to the right. Other than that, they're equal. Okay, so that's the third law. And then I want to say, well, how do I relate this to momentum? Right? Because I don't see momentum in here, and yet this is really important. This is going to be our starting point. I want to relate this to momentum. So do you remember, how do you relate force to, say, a change in momentum? It's the thing we've been doing for a while now.
F net times T.
F net times T causes a change in momentum. So if I could write this, if I could write a negative force on blue times T, right? And then multiply the other side times T, right? F of R times T. That would be a really good thing, because force times time is impulse, and I could go from there. Okay, and that's the idea with this. Now, just make sure that you're okay with this, because algebraically, if I multiply the left side by T, I have to multiply the right side by T. So that's good. But physically what that means is that when the carts are pushing off, they each act on each other for the same amount of time. Right? That's kind of common sense. It couldn't be otherwise. So when they're pushing, each one touches the other one for the exact same amount of time. So it's okay for me to put that T on both sides and multiply it. Okay. All right, so you guys clear on this? So my next couple lines out go to momentum. So if I have the force on red times T, that will be equal to the change in red's momentum, delta P for red. And on the other side, if I've got the force on blue times time with a negative in front, that would be negative delta P for blue. And we're getting somewhere now because we related changes in momentum. I'm going to put both changes on the right side by adding this guy over. So that will cancel it here. I'll have delta P red plus delta P blue. I add those together, apparently I get 0. That actually is one way of saying that momentum is conserved, because it's saying that whatever change happens to red is going to have to be canceled by the change that happens to blue. And because they're vectors, that's going to involve direction. So if I have red, getting positive momentum by being shoved off to the right, that means blue is going to have a change in the negative direction by being shoved off to the left. Positive cancels negative, that equals 0. this is one way of saying that momentum has to be conserved, that the change of one cancels the change of the other. The other way that you can say it, that we said before with energy, is you could break these terms apart, and you could say that delta is mean final minus initial. So you could say P final for red minus P initial for red. You could actually substitute that, right? P final for red minus P initial for red. That's coming from this term. And then for the other one, you get plus P final for blue minus P initial for blue. And what I can do is bring the initial terms to the left side. Like that. So add those to both sides. And you end up with P initial blue plus P initial red equals P final blue plus P final red. Does this at all look familiar to you from when we talked about energy conservation? We said KE initial plus PE initial equals KE final plus PE final. It's really similar. It's really similar. So these two boxes are basically mathematical ways of saying that momentum is conserved. In fact, it's a law of momentum conservation. Okay. I know in last night's reading they walked through that, but it helps to talk about it and ask questions. Diane?
So if I wanted to test this, it would have to always equal 0. If like I would test like this.
That's exactly right. You'd expect the overall momentum to be 0 for the objects that you're looking at in the system. Okay. All right. Two other minor points, not minor points here, but two other things to say about this. Number one is remember that momentum is a vector. Okay. So I'll just put P is vector. Therefore, sign matters. We're already kind of seeing it, right? You have to pay attention to right and left. Right is positive, left is negative. So that's important. We're going to practice with that in the next week in different situations. The second and final thing I'd like to say is that all this stuff that we just said only applies to systems that are completely isolated from the outside world. So, P conservation applies to isolated systems. Isolated, sometimes called closed systems. And that means that you can't have an outside force doing something to the system. If you do, it will change the momentum of the system. So you have to just be kind of careful about picking the system that you're going to talk about. Okay. I don't know if I can get this in video or not, but let's see. So, for example, I'm going to show you two things that mess this up, where the systems are not isolated. Here's one way. Is that, let's say I want to do the explosion, right? But I'm going to actually put a little bit of tape over the wheels on one of the cars. So I put tape across those wheels, right? All right. So now I'm going to put these up next to each other. And let's repeat the experiment. Okay. My momentum right now is 0, isn't it?
Yes.
Friction.
Yeah, it wasn't 0 anymore, was it?
No.
No. What was it? Positive or negative?
Negative.
Negative, because blue kept moving when red stopped. So what happened is there was an outside force acting on the system. That force was friction. Yeah. So friction can mess you up. Friction is real life, right? There's always friction, but if there's a lot of it, you can't count on momentum conservation. Another example would be this. Let's say I wanted to do the explosion again. And let's say I wasn't too careful about my table up there. And my table was sort of crooked. So now I'm going to do this wonderful explosion. Here I go. I'm about to do it. All right, I'm going to do this really great explosion. And I'm going to hit the button and
No one can see that, no one can see
Right.
that, it's okay.
even if I'm really quick about it,
Oh, positive.
I end up with momentum that's all positive because this thing ends up accelerating the other way. And that's because, again, there's an outside external force acting on my system that wasn't there before. What is that force? Gravity. That's a parallel force because I have an incline now. So be careful about that, right? I want to eliminate those external forces because then momentum will change. So, that's the idea. All right.